Hello everybody, my name is Kaushik and I'm going to be presenting this work on behalf of Silicon Synapse Lab and Northeastern University. I'm going to be talking about thruster-assisted inclined walking of legged aerial robot using registrar model and thruster and collocation methods. I'd like to thank everyone working on this project, especially Dr. Ramezani and Dr. Gharib for their mentoring.
Here is a short overview of the hardware that we are working with. ASCII is a multimodal legged aerial robotic platform. It is equipped with 3 degree of freedom legs that can be actuated in the frontal plane, sagittal plane, and can also be extended at the knee using a parallelogram leg linkage. On the aerial side, it has 4 EDFs that are mounted on the torso. This can allow for controlled thrust vectoring using posture manipulation. The robot weighs around 12 kgs and stands 0.7 meters tall with 0 feet. Wing-assisted incline running was evolved in birds to expand their habitat and go across varied terrains. This maneuver is achieved by dynamic posture manipulation and thrust vectoring, unlocking unexplored, rich modeling, control, and robot design opportunities.
Assuming a massless leg, rigid body, fixed slope, and fixed foot locations, we obtain the equations of motion from Euler-Lagrange formulations. Using no-slip constraints for the stamped legs at the fixed foot locations, we can finally get the total state space equations given the following state vector and the control inputs. We use an collocation framework. We start by framing an optimization problem to minimize the tracking error and the control inputs. The decision variables here are the states and the control inputs at discrete points uniformly sampled in a short horizon. Constraint includes the discretized nonlinear dynamics at each point, boundary conditions, and inequality conditions through the horizon defining the friction cone and control input limits. The optimal states are then cubically interpolated to get a trajectory, and the optimal control values are linearly interpolated to form the reference state trajectory. Here you can see an animation of the simulation using the same reduced order model defined for the problem on a 30-degree slope with a friction coefficient of 0.4. The max thrust was about 0.23 newtons. The sample time used for the optimization was 0.03 seconds, whether using an interior point F-min called solver. You can see the final state trajectories for the simulation formed from collocation, as well as the optimal thruster forces and moments in the body frame required to carry out that set trajectory. We were also able to find the ground reaction forces that satisfied the bounds and the no-slip conditions with thruster forces, which is not possible without thruster forces on the 30-degree slope. We compiled the results from simulations on flat ground, 20 degrees, 30 degrees, and 45-degree slopes. In conclusion, we were able to obtain mathematical modeling of wear and introduce a collocation approach to achieve dynamic aids on steep inclines. We were able to study these dynamic aids on 20, 30, and 45 degrees inclines on simulations, and in future we would like to integrate collocation and predictive methods of closed loop wear on hardware with posture manipulation.